Hi everybody, I hope this video finds you well. In today's video, we're going to begin discussing our very first hypothesis test of the term, which is the one sample mean hypothesis test. In this video, we'll talk about what this test is used for. We'll lay out the 5 steps of this test. Remember in the couple of videos ago, we talked about how every hypothesis test consists of 5 major steps. So we'll see how those 5 steps are laid out for this one sample mean hypothesis test, and then we'll take a look at an example of this. So let's begin with understanding when this test is used. So the one sample mean hypothesis test, this is used when you have a single sample of quantitative data that you want to compare against a known or assumed average. So the couple important things to pick out from this is used when you have a single sample, so just one sample. The data in that sample has to be quantitative, not categorical. A good way, of course, to be tipped off that something is quantitative is you see mentions of words like average or standard deviation. Those are terms that only apply when we're working with something quantitative. And we want to compare it against a known or assumed average. So the one sample mean hypothesis test basically allows us to take a set of data, compare the average of that set of data, of that sample, against a known or assumed average that we already believe is correct. Okay, so those are the couple things that you should pick out for helping identify this sort of hypothesis test. So let's get into the steps here. So the first step, we have to talk about the hypotheses. We know that every hypothesis test is always going to consist of a null hypothesis and an alternate. For these one sample mean hypothesis tests, we're going to write these hypotheses as follows. The null hypothesis is going to be written as mu equals some value. And it'll be up to you guys to figure out what value goes here. Now you can actually see that this value that needs to go here is actually matched with that known or assumed average, because what do you do in a hypothesis test? Well, your null hypothesis is what you assume to be true. So whatever that known or assumed average is, that's going to be going right there for our null hypothesis. Our alternate hypothesis is you're always going to have a little bit of a choice. You can believe that the mean is actually greater than, less than, or not equal to whatever that value is. And again, whatever value, this is going to be the same value. Okay? Now, this means that when you go to do your alternate, you actually can choose one of these 3 inequality signs. You can say that you think the average is greater than originally assumed, you think the average is less than originally assumed, or you think the average is simply not the same as what you originally assumed. A little bit of terminology here. If we use this or this, so if we use a greater than or a less than, this is referenced as a one-sided test. In other words, we have a particular direction. We think the average is greater or we think the average is smaller, so we have a particular side. Whereas if we use the not equal to, we call that a two-sided test. And we will see when we get to step 4, the p-value, that it matters whether or not you're running a one-sided or two-sided test. So just keep in mind, when you guys go to do your hypotheses, you have 2 things that you need to do. You need to figure out what value needs to go here. It's going to be the same value in both places. And you'll need to pick the correct inequality sign to basically tell us, do we think that the average has increased? Do we think the average has decreased? Or do we think the average has simply changed? All right. Step 2 is there's going to be a set of conditions. So this is a set of conditions that must be checked for this test to be valid. So the first condition is a condition that is going to be there for every hypothesis test that we talk about. The sample must be random and representative. A lot of times we'll just reference this as being random and representative R&R. To be honest, in our class, we're going to focus more on this condition because as we talked about way back at the beginning of our class, randomness is something we can say, yes, it did happen, or no, it didn't. Representative is something that is much harder to diagnose, so we'll mention it, but we won't really worry too much about it as we're doing sort of problems. In real life, being representative is of course a major issue, but in our class, it's too hard to diagnose that in a small problem set or an exam question or something like that. So as long as we mention it, we'll consider it okay. The second condition is that the sample size must be less than 5% of the population size. Now, I want to say 2 things about this condition too. The first thing I want to say about this is that most of the time, this will not be a concern. Oftentimes, our populations are absolutely massive, like all of the adults in the US, or, all of the people, in a particular state or something like that. So those population sizes are going to be really huge. So coming in under 5% of them is going to be really easy. The only time that this is really a concern is if the population is actually going to be a smaller sort of group. Like if we're studying, say, just the people who live in a small town or just the people who go to a particular university, then we'll have to be more careful about this consideration. The second thing I want to say about condition 2 is, why do we even need to worry about it? Well, this is another one of these conditions that comes up from when we were talking about the sampling distribution. If you think back to the first time we talked about the sampling distribution, we said that in the sampling distribution, in theory, we do the selections with replacement, meaning that the same person might be selected several times. In real-life statistics, when you build a sample, you don't really select the same person several times. If a person's been picked once, they don't get picked again. So in other words, what happens in real life doesn't match what our theory is. So, by having this condition that the sample is very small in comparison to the population, basically assures us that nobody would get picked twice anyway. So by satisfying this condition, we're basically making sure that the way we do real-life sampling is similar to the way that we sort of theoretically consider sampling. The third and final component that we need to check is we need to either check that the data is approximately normally distributed. If we need to do this, we'll often use a stem and leaf plot and actually look at the data and decide if it's approximately normally distributed. Or we can simply have a large enough data set where the central limit theorem will assure us that our sampling distribution will be normally distributed. That means our sample size needs to be greater than or equal to 30. So there'll be 3 conditions we'll need to check each time. First, that it's random and representative. Second, that the sample is less than 5% of the population size. And third, that the data is either approximately normal or that our sample size, is greater than or equal to 30. Once we've checked those conditions, we'll move on to our test statistic. Our test statistic is going to be from the t-distribution, and that's going to be from the distribution that we discussed in the previous video, and it's necessary again because of the estimation of the standard deviation using the sample standard deviation. So how do you calculate this t-test statistic? Well, you're going to be doing x bar minus mu over s divided by root n. Now, something I want to just make a little note of, let's make a little chart of what each of these things are. X bar, as we know notationally, that is our sample average. Mu is going to be that null hypothesis. That's why the null hypothesis tells us what value we're going to assume for mu, because we'll need that for the test statistic. S, as always, is the sample standard deviation, and n is the sample size. This calculation here should look very familiar to you guys. What you're effectively doing is you're calculating something very similar to a z-score. You're measuring how different the average in your sample is from the average you assumed was going to happen in the null hypothesis, divided by the standard deviation from the sampling distribution, the original standard deviation divided by square root of n. Again, the only reason that this guy here is a t rather than a z is because this is the sample standard deviation, which in real life is all we're going to have access to. Once you calculate the test statistic, we'll be moving on to step 4, which is the p-value. Remember, the p-value is the probability that we would get results as or more extreme than our data, assuming the null hypothesis is true. So we're going to calculate the p-value using table C because our test statistic is going to be a t-test statistic. For table C, we need degrees of freedom, and we're going to be using degrees of freedom equal to n minus 1. So our degrees of freedom is always going to be 1 less than our sample size. When you go on to table C, which we'll see in just a few moments when we actually do our first example, at the bottom of table C, there is a part that says one-sided p-value or two-sided p-value. You select which one you're going to use based on HA, the alternate. So if you're running a alternate that is a greater than or less than a one-sided test, you will use the one-sided p-value. If you're running a two-sided test, the not equals to, you'll use the two-sided p-value. And again, once we get into our examples, you'll be able to see that. A couple quick notes about this. First of all, sometimes this test statistic will be negative because the sample average will be smaller than the null hypothesis. Just like we did when we were doing critical values and correlation, if this test statistic is negative, we leave it as negative, but when we look it up on our chart, we will use the absolute value. The second note is that, as we'll see when we begin to do our examples, sometimes our degrees of freedom doesn't show up exactly on the chart. If the degrees of freedom cannot be found on table C, then you will always round down to the next available degrees of freedom. So we'll see an example of that in just a few moments. Finally, step 5. This is where you make your conclusion. We mentioned how making the conclusion is based on basically detecting whether or not the p-value is low, meaning that you have strong evidence, or if the p-value is high, meaning you really don't have any evidence. So we do that via a comparison. If the p-value is less than alpha, which is what's called the level of significance and will be defined for each problem, if the p-value comes in less than alpha, then we will reject HO. Rejecting HO is often called a statistical conclusion. We will say reject HO, and then we will write out that this means that we have significant evidence for our claim HA. If the p-value we calculate is greater than the level of significance, then we will fail to reject HO. This will mean that we do not have significant evidence for HA. So I just want to call your guys' attention to this before we do our example. Notice that the statistical conclusion is always in terms of HO. You either reject HO or fail to reject HO, whereas the statement in terms of evidence is always in terms of HA. If you reject HO, you have significant evidence for HA. If you fail to reject HO, you do not have significant evidence for HA. So this lays out the sort of 5 steps for a one-sample mean hypothesis test. In this video and the next, we'll go ahead and do some examples of running this test, and then in later videos, we'll learn new hypothesis tests. We'll learn how to do this with multiple samples. We'll learn how to do it with categorical data, so on and so forth. But as we do this more and more, what you guys will see is that we will always have these same 5 steps. Individual components will shift a little bit, but they'll always be under this structure of these 5 steps. Okay, so some of this is probably a little bit unclear. Hopefully most of the notation makes sense, but how to do each piece might not be totally set yet. So let's get into taking a look at an example. All right, so for this example, we're going to say, according to the FDA, a standard 18-ounce jar of peanut butter is allowed on average to contain 510 bug parts. Now, this is an unfortunately true fact. If you guys want, you can research that the FDA has all these pretty horrendous limits on what is allowed in peanut butter, such as like bug fragments, rodent hairs, etc. This is a little bit scary, but it is absolutely true that in a standard 18-ounce jar of peanut butter, you're allowed to have at most 510 bug parts. This is mainly because peanut butter is processed in these giant open air sort of vats where they churn the peanuts together. And unfortunately, anything that falls in there, well, it is also added to your peanut butter. So we're going to suppose that we're tasked with investigating if a company, in this case Cheapo Peanut Butter, is operating over this FDA limit. So to study this, what you do is you visit each of Cheapo's 3 main factories and you randomly sample 20 jars of their peanut butter from each. So since you went to 3 main factories and took 20 jars, you then take your sample of 60 jars, 20 times 3 giving us our 60 jars, and we find that the average number of bug parts in these jars is 523 with a standard deviation of 37. What we're going to do with this is we're going to answer a couple questions. First, we're going to do a little review and just remind ourselves what the name of the sampling technique was here. We sort of built this sample in a very specific way, so we'll remind ourselves about that. Then the majority of this problem will be in B, where we will carry out at alpha equals 0.05. Notice the alpha is stated in the problem. A hypothesis test to test the claim that Cheapo peanut butter is operating above the average number of bug parts allowed by the FDA. And then finally at the end, we'll do a little bit of sort of analysis of the type 1 and type 2 errors in this situation. Okay, now a couple things I want to note here before we get into the main part of this. Notice what we're really doing here. We're saying that according to the FDA, the average is supposed to be at most 510. And in our sample, we found 523. So you might say to yourself, why are we not just saying, well, it was 523, so that's about 510, so we're ready to sort of accuse them that they're above this average. Well, the idea is that this is only a sample of 60 jars. So maybe these were just some jars that happen to have more bug parts than normal. Maybe in general, right? Maybe, in other words, Cheapo might just argue this is some bad luck. So the whole point of this hypothesis test is basically to analyze how different this 523 is from this 510 based on the size of our sample and the amount of deviation we expect. If this is really different than this, then we'd be saying, okay, we have enough evidence to accuse them of something. If this turns out to really not be that different from this, then we might end up saying we can't really accuse them of much. So that's the whole point of running this hypothesis test. So let's go ahead and get started with this. First of all, we want to talk about the sampling technique. So this is not going to be important in terms of running the hypothesis test, but let's just remind ourselves. So what were sampling techniques? Well, we had a variety of them. We had the simple random sample, we had systematic, we had stratified, we had cluster, and we had convenience. Now, we know it's not going to be convenience because convenience is not valid for statistical sort of analysis. And we know that we're going to be doing statistical analysis, so it's not going to be convenience. So let's recall how we sort of did this. Well, we visited each of Cheapo's 3 main factories, and we took 20 jars from each, and we combined them together for 60 jars overall. Since we took 20 jars from each of their 3 main factories, this would be an example of a stratified sample. So this was stratified, and the strata here were the factories. In other words, whenever you have a bunch of small samples that you sort of put together to make your overall sample, well, that's stratification. And in this, the reason stratification would probably be used here is to make sure that we get some data that represents each of their factories. In other words, we wouldn't want them to say, oh, you're only allowed to visit this one factory, only test the jars from there, because maybe one of their other factories is really, really dirty or really bad. So by taking some jars from each factory, in other words, using a stratified sample, we have a more representative sample in this case. Okay, now we're ready to start the hypothesis test. So, what type of hypothesis test is this going to be? Well, it better be the type that we talked about, but let's see if we can understand why that is. Let's think about our data first. So our sample is a sample of 60 jars, so we have 1 sample, and we're calculating things like the average number of bug parts. The number of bug parts in a jar, that's going to be a quantitative variable. So we have a single sample of quantitative data, and we're going to be comparing it against the average that the FDA allows. So a single sample of quantitative data against a known or assumed average, that is exactly the 1 sample mean hypothesis test. So this is going to be a 1 sample mean hypothesis test. 1 sample quantitative data versus known/assumed average. Perfect. So later on, this step of identifying the type of hypothesis test will be more important because we'll have more hypothesis tests. Right now, we only have 1, so of course this identification turns out to be that 1. But later on, we'll have to be more careful because we'll have several different types of hypothesis tests and we'll have to choose the correct one. In this case, it will be a 1 sample mean hypothesis test. So let's begin to write this thing out. First step that we need to do here is we need to come up with our hypotheses. So what are our hypotheses going to look like? Well, we're going to have to talk about our null and our alternate. We know that the format is going to be mu equals something, and then mu some inequality sign and that same value. So again, when we get to this step with the hypotheses, there are 2 things to do. We need to figure out this value, and we need to figure out the inequality here. So let's think about figuring out this value. In other words, what is the null hypothesis here? Well, remember, the null hypothesis is the sort of known or assumed value. So if we look back here, right, we're looking for an average. There's only 2 averages that are mentioned in this problem. There's the average that's allowed by the FDA, and there's the average from our sample. The null hypothesis is about your assumption, so it can never involve your sample. So it definitely can't be this. It's got to be the 510 because that's what we're going to assume they're doing, right? If you think about accusing a company, you have to sort of give them the benefit of the doubt at the beginning. You have to assume that they are operating within the limits. So we're going to use this average of 510 as our null hypothesis. So we'll have 510 and we'll have 510. Then we have to figure out our claim. What are we claiming against them? Are we claiming that they're above, below, different from the limit? Well, we can read our claim right here. The claim says that cheapo peanut butter is operating above the average number of bug parts allowed by the FDA. Obviously, it makes sense that we're worried that they're above the limit, not below the limit. So the alternate here would be mu greater than 510. We're going to assume that they're operating at the limit, but we are concerned that they might be over the limit. As a quick note here, what we should see here is that this means that we are running a one-sided test because we use the greater than, which means it's going to be one-sided. When we get to step 4, the p-value, we'll have to remember that it was a one-sided test. Okay, let's go ahead and talk about the conditions. So, conditions. The first condition is that with the data, our sample is random and representative. So let's go back up in here. Again, we're not going to worry too much about representativeness because it's very hard to check when you only have like a little paragraph of information. We're really just making sure that it was done randomly. And that's stated right in the question. So all we're going to do is put in parentheses next to this, stated, put a little check mark, and move on to the next condition. The next condition is we need to make sure that our sample size is less than 5% of the population size. Okay, well, let's think about if we know what these things are. Do we know the sample size? Well, we better because we're going to use it later on. So what is our sample size? Well, our sample size is you took a sample of 60 jars. So that right there is our sample size. Do we know the population size? Well, the population size would be all of their jars of peanut butter. Unfortunately, there's no information in this question about how many jars of peanut butter this company has produced. But if you think about it, producing jars of peanut butter is not something where they're only going to produce a little bit. They're probably producing thousands or hundreds of thousands of jars. So there shouldn't be any concern here. So all we're going to do, as just to make sure we understand what we're sort of saying here, is we're going to make a comment that there's lots of cheapo peanut butter. Check. Now, maybe we don't know that for sure, but it seems likely that that's the case. And all I'm looking for in this situation, if the population size isn't given in the problem, is for you guys to just correctly identify what the population is. In this case, it would be all of the cheapo peanut butter, and certainly there's lots of that. So we're safe in assuming that our 60 jars represent only a very, very small portion of the overall population. All right, condition 3. Now, condition 3, we said that the data has to be approximately normal. Unfortunately, if you read through this, there's no mention of approximately normal in here. But luckily, we can use the other way of checking it. We know that our sample size, n, is greater than 30. So for condition 3, all we need to say is n equals 60 is greater than or equal to 30. So we're all good. So all 3 conditions are satisfied, so we can move on to the next step. Now, this is also a good moment to sort of just mention to you guys, in this class, anytime you guys are asked to run a hypothesis test, the conditions are going to be satisfied. So the question is not for you guys to figure out whether or not these are satisfied. The real thing that you're being asked to do is to make sure you can explain, even just briefly, why the conditions are met. I'm not going to throw any trick questions at you where the conditions aren't satisfied, but you have to be comfortable saying why, in this particular situation, they were satisfied. Okay, so let's go ahead and talk about the third step. So for step 3, we're going to go ahead and get our test statistic. So for our test statistic, we're going to be using that formula, T equals x bar minus mu divided by S divided by root n. Well, you'll have to make a little list of the 4 things here that you're going to need to know to plug into this formula to calculate this. You'll need to know x bar, mu, S, and n. A couple of these things we've already used. We had n equals 60, so we know n is 60 here. We also have already written down mu, right? We said mu equals 510. That's why when we're doing this, the null hypothesis is always an equality because it tells us what we're assuming for the average here, for the population average. So that'll be 510. The only two things missing are our sample average and our sample standard deviation. So if we go back and look at the problem, we were told that we take a sample of 60 jars and find that the average is 523 and the standard deviation was 37. So these two pieces about our sample are what we're going to use here. So our X bar here is 523 and our standard deviation is 37. So let's plug this stuff in. We'll get T is 523 minus 510 over 37 divided by the square root of 60. Now, to make this a little bit easier, I think we'll take this guy and we'll sort of bring it up here. For typing this in, what I would recommend, if you're comfortable using your calculator, there are some tricks to doing this all in one sort of line, but what I would do is I would do the numerator and the denominator separately. So take 523 minus 510 and then do separately 37 divided by square root of 60. If you do that, you should get that T. Up top, we're doing 523 minus 510, so we should be getting 13 up top. And then in the denominator, we're doing 37 divided by the square root of 60, which should give us 4.78 here, 4.78. Okay, then go ahead and do the division. So we get that T, 13 divided by 4.78. Looks like it should come in as at about 2.72. Now, if you do it all in one go in your calculator, you might get a slightly different t-value. That's okay, right? As long as it's close to 2.72, you'll be all good with what we're doing here. So that is our test statistic. What this is really telling us is it's telling us that our sample, where our sample had an average of 523, compared to the expectation of 510, is about 2.72 standard deviations above the average. So that's pretty far. That's almost 3 full standard deviations beyond what we expected. Now we're ready to translate that into a p-value. So step 4, we'll talk about the p-value. So we're going to be using table C, and we'll jump to that in just a second. But before we do that, we will need to use our degrees of freedom. Degrees of freedom is always n minus 1. In this case, n is 60. So the degrees of freedom here is 60 minus 1 equals 59. Also keep in mind when we go to use table C, you'll need to remember, is it a one-sided or two-sided test? Well, it is one-sided here. So we're looking for the one-sided p-value. So we'll jump to the table now. Keep in mind that our t-value was 2.72. So let's go ahead and take a look here. So there's our table C. If you look at table C, you have degrees of freedom here, and you have all these different t-values inside. Don't worry about what's on top right now. Just think about the degrees of freedom and your t-values here. So remember, our degrees of freedom was 59. So if we scroll down, well, unfortunately, we see that 59 isn't there. We have degrees of freedom 50 and we have 60. Remember, we said that if the degrees of freedom is ever not there, what you're going to do is round down. So in this case, degrees of freedom equals 59, use 50. So we're going to be using the lower one. And this is called the conservative approach. It's just going to be what we always do in this. So we're not rounding to the nearest one. We're always rounding down. So 59 would become 50 here. So we're going to be using this row here. In this row, you're going to find where our t-value is located. Remember, our t-value was 2.72. So if we do this, right, 2.72 is above all of these guys, but it is not past that 2.937. So 2.72 would end up being somewhere right like there. So we'd find ourselves in between the 2.678 and the 2.937. Then we're going to follow this column down to where it says one-sided P and two-sided P. We want to use the one-sided P, so we will find ourselves right there. So we are now located right here. This then tells us where our p-value is located between. So we know our p-value is between 0.005 and 0.0025. One thing you guys should notice is that these p-values get lower as you go this way. So this is the low end of the range and this is the high end. So when we go to write the p-value, we'll always write this number over here first. So our p-value will be between 0.0025 up to 0.005. Let's go ahead and record that. So in this case, we just figured out that our p-value here is between 0.0025 is smaller than our p-value, which is smaller than 0.005. So when we do one of these hypothesis tests, we do not get an exact value for the p-value. Instead, we've just figured out that the p-value is somewhere between 0.25% and 0.5%. So it might be something like 0.3% or 0.4%. We don't know for sure, but we know it's in this range. Okay. Let's go ahead and make our conclusion then. The conclusion. So we take this p-value and we compare it against the alpha, which was 0.05. How do we know the alpha was 0.05? Because that's stated right in the problem. So how does this p-value up here compare to this? Well, we don't know exactly what the p-value is, but we know that the p-value is smaller than 0.005. So if it's less than 0.005, it's certainly less than 0.05. So we can conclude that the p-value is less than the alpha. So in other words, our p-value here is very small because it's even smaller than our alpha of 0.05. What conclusion do we make when the p-value is less than the alpha? Well, if you go back and you look at our little step 5 here, if the p-value is less than alpha, we reject HO and we have significant evidence for HA. So we would finish this thing up by saying reject HO. So you would say that, and then you would write significant evidence that cheapo peanut butter is above the FDA limit on average. And it is super essential that you make use of that word on average, or that phrase on average, in your conclusion, because this is a hypothesis test about averages. So we are not claiming that every jar of cheapo peanut butter is above the FDA limit. That's not something we're doing at all. We didn't even have the individual amounts in each jar. But instead, what we're saying is we are convinced that they are operating on average above the limit. Some of their jars might pass, some might not, but we're saying on average, they're above the limit. So this gives you guys your first example of running one of these hypothesis tests. Every time we do this, we'll always go through all 5 of these steps here. Couple things I want to point out is in this phrasing in the conclusion, these two things always go hand in hand. If you reject HO, you'll be saying that you have significant evidence. In examples where we fail to reject HO, we'll be saying no significant evidence. So these two things are really saying the same thing, just one is based on the null, and this sentence is based on the alternate. Okay, what is the meaning behind all of this? Well, what we're basically saying is our average of 523 compared to the original assumption that they'd be at the FDA limit, 510, turned out to be a sample that was close to 3 standard deviations above where we were expected. We found out that the chance that that would happen, if they're really operating at the FDA limit, is somewhere between only 1/4 to 0.5%. So in other words, the claim that this just was bad luck amounts to us having to believe that we just observed something that's supposed to happen only 0.5% of the time. Rather than believing that this was just sort of bad luck as a sample, we're convinced that they're actually operating above the limit. Are we convinced that they're operating at 523 per jar? Not at all. That's not at all what we're testing. We're just convinced that they're above the FDA limit. Okay, let's wrap this example up and wrap up this video by just briefly discussing the type 1 and type 2 errors on this. So we'll do that on the next page here. So let's talk about the errors. So type 1 and 2 errors. Now, I want to make a note here. When you guys are asked to analyze the type 1 and type 2 errors, all you really need to think about are the hypotheses. So just because I moved on to a new page, I'm just going to restate the hypotheses. So we're going to rewrite hypotheses. So remember, our null is that we're saying that they were operating at the FDA limit, 510, and our alternate is that they were above 510. Okay, so let's go ahead and talk about what the type 1 and type 2 errors would be. So let's talk about the type 1 to begin with. What does type 1 mean in general? Well, type 1 is when you reject HO, but HO is true. Okay, now to help you guys sort of understand this, what I'm going to do is I'm going to write out each of these pieces in this situation, sort of in a different color, so you can see how you would phrase this. So let's start by talking about what rejecting HO means. Remember, rejecting HO means you're getting rid of this, and you're going with that they're above the 510. So this would mean we believe there is significant evidence that on average, cheapo peanut butter is above the FDA limit. Okay, so this would be where we're rejecting HO. Now we need to talk about this part. But in reality, HO is true, meaning they're actually right at that FDA limit. But in reality, they are at the FDA standard. Okay, that's a very formal way of describing what the type 1 error. In real life, what would be the result of this? Well, this would be where you say that there's evidence that they're above the FDA limit, but in actuality, they're operating within normal standards. If you think about what would happen here, this would turn into a false accusation. This would be where you would decide based on your research that they should be investigated or punished by the FDA, but in reality, they're not doing anything wrong. That would be a type 1 error in this situation. Let's talk about a type 2 error. So a type 2 is where you would fail to reject HO, but HO is false. So I'm going to do the same thing as I write this interpretation. I'll write this part, what we think, in red, and what is actually true in blue. So this is where we believe there is no evidence that on average cheapo peanut butter is above the FDA limit. So notice that failing to reject goes hand in hand with no evidence. But in reality, okay, that's just a little bridge statement. Well, HO is false. So HO is false, and they actually are above the limit. So, but in reality, they are above the limit. So what's the real life sort of consequence of this? Well, they are allowed to continue producing, I guess, what we could call bad peanut butter. Right? So notice that both of these errors are certainly bad. Nobody wants to make a false accusation against somebody, and nobody wants to let a bad product continue to be on a market. So, as always, errors are bad things. Do these always happen? Not necessarily, but we just want to be aware of what the consequences of each type of error would be here. So, in later videos, we'll continue to do some more examples of running this hypothesis test, as well as doing some further error analysis.